Chapter 2, Atoms and Elements. So let's think about your pencil. You have graphite in your pencil. It's not lead. It's graphite. It's made out of carbon. If you took the lead, broke off a piece from the end of your pencil and cut it in half, and took one of those pieces and cut it in half, and kept doing that, if you had a small enough knife, how far could you go? Could you keep cutting something in half forever? Is it infinitely divisible? Or would you come to a smallest piece? And that was a question that people thought about for a while. Anybody been to Legoland? No? Oh, okay, at least one person. The rest of them are deprived, don't you think? Legoland's cool. They have this area where they have made the 7 wonders of the world and many other things out of Legos. And so you can see the Taj Mahal, and I don't know, it's like 10 feet tall or something. It's made out of Legos. So if you look at it from a distance, it looks like the Taj Mahal. As you get closer, you see it's made out of Lego bricks. But if you took the Lego Taj Mahal and broke it in half, and then broke a half in half, eventually you'd get down to a single Lego brick that you couldn't take apart. Right? Well, it turns out with regular matter, you also get down to a smallest piece. And that smallest piece is called an atom. And that word atom comes from the Greek word atomos, which means indivisible. When you get down to a carbon atom, you can't cut it in half and still have carbon. All matter is composed of atoms. To understand matter and its behavior, we have to understand what atoms are. And that's what we're going to talk about in this chapter. Okay, 1827. A guy named Robert Brown was looking at pollen grains suspended in water. And there were even some smaller particles that came off the pollen grains. And he was looking at them and noticed that they jiggled around. So let's watch this. We've got a couple of movies today, along with the train. So this is what he was looking at. These little particles, and they're jiggling around. Very exciting movie, right? Maybe not so much. Let's get back to this. So we saw these little tiny particles, visible with a microscope. They're jittering. What's causing that? Why are they moving? Is the table shaking? Are they alive? Living organisms? You don't have to have an answer. Well, Robert Brown initially thought they might be alive. Further investigation showed that they were not alive, and so he concluded that the source of that motion must come from outside the particles. It must be something else pushing them around. So this is a mystery. And this phenomenon that he observed of these little tiny particles jittering like that is called Brownian motion, because Brown first noticed it. In 1905, this was a while later, Albert Einstein developed a theory to explain Brownian motion. It explained it as a result of molecular bombardments of the particles due to the thermal energy of the surrounding water. We've talked about how particles in a solid, a liquid, or a gas are moving, right? At the very least, they're vibrating. Temperature is a measure of how much they're moving. So the idea here that the water molecules in the liquid are hitting those particles and causing them to move. It's a little bit like throwing a beach ball into a crowd. And everybody, just bats at the beach ball or it bounces off their head. And it moves around the crowd in a very disorganized, random way. So that's what's happening to these particles. This infers, doesn't prove, but suggests the existence of atoms, of individual particles. Einstein and others did more work that removed the doubt about the particulate matter of nature. Until then, there was still debate about whether atoms existed or not. We couldn't see them. But this does remove any doubt about that. Then we're going to jump forward to the 1980s. IBM researchers in Switzerland developed a technique called scanning tunneling microscopy. And this is a cool technique. So you've got this tip, very sharp tip, and they're passing an electric current through this tip across a little air gap and into the surface that they're examining. And they have a computer that's moving this tip back and forth in a pattern, and they're controlling the tip so that this distance is always the same. So they do that because they can do that because the amount of current that flows here depends on the distance. If you pull the tip further away, the amount of current flowing through that air gap will go down. So they move it across, keeping the current constant. And so as they come across here, there's this little, like a ledge here of atoms. This instrument senses that, raises the tip up. And so you can get an image of the surface, even though it's far too small to see. So using scanning tunneling microscopy, we can get images of individual atoms. And you can actually move atoms and make patterns. And so here they've made the Japanese kanji characters for the word atom. And these red little triangular kind of things are iron atoms, and the background is a copper surface. And so they wrote atom in Japanese with atoms. Yes, this is kind of, scientists do have sort of a twisted sense of humor. And sometimes they do things just because, hey, let's see if we can do it. Okay, so I've got a couple other videos to watch here. This is a guy from IBM explaining how this works.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
Anybody have any questions? Yeah.
How long did it take them to rewrite atom?
That's a good question. I don't know how long it took them. It was certainly much longer than just writing it with your hand, because moving each atom probably took at least a couple minutes. Yeah, that's a good question. So you can write things with it, or they went a little further and they made a movie, a stop motion animation movie with atoms. My kids have done this with Legos, but I think this is cooler. The world's smallest movie. The world's smallest movie. If you're interested in how they made that, there's another YouTube video that shows how they made the movie. It's interesting, but it's a little too long to take up lecture time. Any questions? Now, atoms do not actually look like this. They're not little cone-shaped things. We believe that they're actually spheres. But because of how we're imaging these, this is the best resolution we can get. So just to give you an idea of how small atoms are and how small those letters are, have you heard of the Library of Congress? They have basically copies of all the books that have been published. 35 million books on 840 miles of shelving. Okay, that's a lot of books. If you took all the words in all of those books and wrote them in letters the size of those kanji characters with the atoms, all the words would fit in an area of 5 square millimeters. 5 millimeters is half of a centimeter. Half of a centimeter square, you could put all the words in all the books in the Library of Congress. Does that blow your mind? That blows my mind. Atoms are mind-bogglingly small, crazy small. So, another way to think about an atom is it's the smallest identifiable unit of an element. We talked about what elements are. There are 91 different naturally occurring elements, and then there's over 20 synthetic elements. These are not found in nature, they're man-made. And there's people busy working away trying to make new ones. Is there any real constructive purpose in making new elements? Probably not. But not all science has to be. It doesn't have to have a practical purpose. Sometimes we do things just for the sake of seeing if we can do them. And often in the process of doing that, we learn new things about the universe. And so that can be really helpful. Okay.